Okay, so this is where we left off last time, and there's only 3 slides left in the chapter. And so the quantum numbers we have discussed before had been up to here, and they had created these wonderful, really neat orbitals, right? And so what these are is the magnetic field interactions that are happening due to the positive charges of the nucleus and the negative charges from the electrons. And so as you build up these orbitals, you get some kind of interesting interactions where your stabilities change and where the electrons are likely to be located change based on those interactions. Have you guys ever seen the magnetic field patterns if you take two magnetic fields and then you throw iron uh, dust in it? No? Oh, that's just sad. Have you guys seen anything that gives you indications of magnetic field patterns and magnetic field interactions? Jeez. I just so disappointed in you all. It's literally freely available on the internet and YouTube. Nobody does like Veritasium or something? Don't even know what Veritasium is, do you? It's a it's one of the more popular channels on the internet. You guys are killing me. What the heck are you doing with your time? Studying my class? All right. So anyways, when you start looking at multiple directional interactions between magnetic fields, they don't become such easy patterns as like further more stable or less stable. It just gets more complicated because you start getting interactions where you're starting to look at destructive and constructive interference, right? Kind of like the flashlight, right? It's not super simple, bright, dark. There's like bright, less bright, dark, then another dark sometimes. And it gets a bit more complex, right? Yeah. And so that's what we're seeing right here. That's actually what creates these kind of weird orbital shapes. You'll notice at the beginning, they're really simply shaped, right? Literally less stable going out, okay? And that's your s orbitals, right? And as we add in those s orbitals, we start getting a more complex shaping, okay? Because the electrons in those s orbitals create that complexity, right? And so we get the p orbitals, right? And they have different directions to them, okay? And we can add these orbitals in as we get further and further out from the nucleus. And why can you do that? Why do you have more orbitals that can be added? Okay, so the volume of something, does that change the same as the surface area? No, surface goes up in squares, right? Volume goes up in cubes, exactly. And so as we're adding more volume, we get more space within our orbitals, and we also get more complexity to these orbitals because we start getting things like the p orbitals are now affecting the next orbitals out, right? And so you create the d orbitals that fit in those. And then you create, after that, you have d orbitals that are affecting, and the electrons in them affecting the new orbitals. You get the f orbitals, okay? And so these get pretty weird energetically. For example, the d orbitals don't fill in when you first create them, do they? Okay. So you fill in the 1s, then 2s, then 2p orbitals, right? And then you fill in the 3s, and then what's after 3s? Okay, let's go back to orbitals real quick, because I have a funny feeling that your guys' general chemistry didn't really. Anyways, or maybe you don't remember, I don't know. But either way, so the periodic table is organized based upon the orbitals. So see this block right here? How it looks like a little tower onto itself? That is an s orbital. You're filling in an s orbital every single period. Okay? And that's why it's 2 elements wide. Because an s orbital has 2 electrons worth of space. Okay? And so literally, fill in the s orbital, that's done with the block. Then you move to the next one. On period 1, you only have space for 1 s orbital, don't you? And that's it. You don't have space for anything else. And so we go down to the next period, the next energy level. We have more space. Okay? And so we put in an s orbital. That's lithium Be, Li-Be. Everybody okay with that so far? And then what we do is we start filling in the extra space with p orbitals. And those are locations that you can fill in with electron density, right? Okay. And so we literally fill in 6 electrons worth of space, don't we? That is 3 orbitals. That is the px, py, pz, isn't it? Can everybody see that okay? Okay. Very obvious, isn't it? By the way, you guys want an MIT thesis question you can really stump people with? Yeah? I promise you, you can ask PhDs in chemistry, and there's some of them who won't be able to answer this. Ready for it? Okay, what would happen if we removed one dimension from space? So space was only 2-dimensional.
We die.
And what would happen to pure activity? Like, we could theoretically have 2-dimensional space. We would not be designed as we are, but yeah. So why is this block 6 electrons wide? 6 spots. X, Y, and Z, right? If we removed one of the dimensions, what would happen? This would only be 4 wide, wouldn't it? And the d orbitals would also have to have all of one of the dimensions removed. So see the ones that have contributions to one of the dimensions? Those would disappear or partially disappear. And so what would happen is this would actually become essentially a pyramid in shape. And we would have actually new orbital setups, D, F, whatever you want to use after that, that would start adding on to the bottom. Okay? Okay. And so notice that we get to the 3rd period and we start filling in 3s orbital, and then hey, what happened to D? When does D get created?
At 4s.
It gets created at 3D, doesn't it?
Oh.
Yeah. So this actually gets created on this period. D's there. Doesn't get used. It's too high energy. Okay? And that's because it's fitting into the sort of weird edge cases of that orbital that would end up being higher energy because the other spots are filled with electrons, aren't they? And so those end up higher energy than a 4s orbital would be. Okay? Or a 3p orbital would be. Right? And so we fill in the 3p, then we go to 4s, then we start filling in the 3d. And the same thing happens. This is the 4f period right here. At LA. Right here. We're filling in the f period. The f orbitals. But it's actually the 4f. It's created on the 4th period. We just don't fill it in until way the hell down there. Because it's very high energy. And that's because the shapes and the interactions with the other orbitals. It ends up being very high energy. Now, one of the reasons I point this out is when you start filling in d orbitals and stuff, you will notice that as you pair electrons together, they actually sometimes jump down into the s orbitals, or they jump up from the s orbitals into the d orbitals. Okay? And if you remember your rules, those were those edge cases that you had to learn in Gen Chem. Okay? All right. And so that's actually what you're seeing in these cases. Okay? And we've now hinted at the next quantum number, haven't we? Right? So what if everything was the same about 2 electrons? They had the exact same quantum numbers. What would happen? They'd be indistinguishable. They'd be the same things, wouldn't they? I mean, literally just same place, same time, same everything. Yeah. And so what would end up happening is you can't actually do that, can you? They would actually end up constructively, destructively interfering with each other, and it just can't happen and be stable and actually exist. Okay? And so what you actually see here is that we have one more quantum number that we have to add. this is what allows us to have 2 electrons per orbital. Okay? And this is why we talk about these orbitals as having 2 electrons in them, is because we have what's called the spin quantum number. Typically, this is thought of like you have a planet spinning. Okay? And that's the analogy that's used. It is not necessarily the reality of the physical object. Okay? In fact, at the scale of an electron, we can't actually like watch it do stuff. We're like watching it and it's gone. Oh, it's over here now. It's gone. It's over here now. Okay? And that's happening on the nanosecond scale, and so we can't even get small enough to see it in the first place. We can't keep track of it. We can't pin it down enough to actually tell where it is all the time. So that's not something we could actually see, and that doesn't really make sense because they're not really spherical objects like a planet or something, okay? However, this is a very, very good analogy, and it works really well for math. And so there is something that's analogous to it that we're looking at, okay? And so this is spin 1/2, positive 1/2, and spin negative 1/2, right? And if you use the physics right-hand rule, you can also call this spin up, spin down. Though, again, because we're looking at electrons popping all over the place, what is up and down is a little... But a better way of thinking about this is the direction of the magnetic fields that we're seeing from these electrons. Did that make sense? So one of the things you can actually do with this is you can actually do a very powerful magnetic field, pulse it in, and cause a bunch of these fields to arrange in one direction, and then watch them move off that direction, decay. So what we're actually looking at, have you guys ever heard of the right-hand rule? Yeah? Okay, so the right-hand rule is when you have electricity moving through a wire, the magnetic field is actually like this from that. Okay? And so you get the same sort of thing because, again, electricity is electrons moving, isn't it? So this is actually what is part of that, part and parcel. This is the spin of the electrons. When you have 2 electrons in an orbital, they have to have the 2 different spins. You have to have one spin up, one spin down. That creates a difference in energy, very small difference in energy, and that's why they're not the exact same energy, exact same everything. Okay. Okay, so this right here is a conception of the electron spin, of course, because we have no way of actually dealing with that. How we actually start observing these things is we use right here this experiment. And so we take a beam of silver atoms, and so what we do is we put it through a magnetic field that has a little wedge. Can you guys see the wedge in the field? It's a wedge north magnetic field and then a box south magnetic field. Okay? Okay. And so what we see here is if they all had the same spins, okay, on everything. This wasn't actually done to try to find the spin on electrons, by the way. This was actually a test that was supposed to be done for the atoms. The reason this is happening is silver, if you look up at silver, has an unpaired electron. Okay? And so we have an unpaired electron in silver. You could do this with anything that has an unpaired electron, right? And so what we ended up seeing when we do this is that if they're all the same and all the electrons are the same, then they're all going to deflect in the same direction, or they won't deflect at all, right? Okay. If we had it where we could have like a some sort of difference, but it was some probability difference, we would deflect unevenly, 30%, 70%, that sort of thing, right? In this case, though, we actually deflect evenly. So what we get is a straight up split. Okay? And so what does that mean if you get a straight up split?
Turning opposite, or they're kind of like opposite directions.
Yeah, you're atoms in this case that has one unpaired electron have two slightly different magnetic fields that have different directionality to them, right? Okay, and those populations are even among these silver atoms. Okay. By the way, this is a furnace. Does anybody know why this is a furnace? Yeah. Yeah, we have to heat these so they become gaseous and we can shoot them out of the furnace. Okay? And so we're making a silver beam. Yeah. Silver particle beam, right? Okay. All right. And so this would actually have been the classical prediction right here, where they all deflect one direction because they all have one unpaired electron, and so they should have a magnetic field, but it should all be the same magnetic field. They were not the same magnetic field because there's actually two magnetic orientations that can happen with the electron, despite the fact that it's negative. There's two directionalities to it. Okay, and so this right here is the electron density measurements undergoing a topographical map for these electron densities. And what we can see is this is a better representation that makes it look more like a three-dimensional shape. And so this right here would be your 2s orbital, right? See the s orbitals? Okay. And what we're seeing is the different magnetic field strengths within that orbital. Okay. And notice if you looked at the electron clouds, you see like lighter shading, darker shading. What does that actually represent? Magnetic field strengths, which is the probabilities of finding the electrons in those areas, right? Higher strength of the magnetic field, more probability of finding electrons. Okay. This right here is then, what sort of orbital is that, by the way? This one's S, right? Yeah, so those are the lobes of the p orbital, aren't they? Yeah. And so again, what we're seeing here is, again, the isosurface, the strengths of the magnetic fields and how they're distributed. Or another way of saying that these are the wave functions. Okay? Okay. All right, and so these right here are the different SI units versus their atomic mass units. This is a nice summary of this. It's very useful for doing problems whenever you have to deal with these things. Okay? And so I gave you a copy there. It's also in your book. If you ever want, so you don't have to do it yourself, you can copy and paste that onto something and have it available. Okay. All right. This right here is the reciprocal wave number, by the way. That's what that's referred to as wave number, or reciprocal centimeters. Very, very common energetic unit when you're talking about spectroscopy. Probably the most common in terms of infrared and Raman. This is unfortunately not a super commonly used number, except when you start talking about like nutrition. And they call it capital C calorie, right? Which is a little sad and weird. It's actually very convenient. This is hertz, by the way, very commonly used in things like microwave. You guys know this because of 5G, probably. 5G is what? 5 gigahertz. That's the frequency of the radiation. What's 4G? 4 gigahertz. It kind of falls apart after that. So, yeah. 3G and 2G are kind of ish in the ballpark, but not really. Yeah. But anyways. Yeah, I think that about does that. Anybody have any questions? Okay, got a little bit good review. Now the next lecture